Good morning, class, and welcome to our continuing lectures on climate dynamics, climate variability, and climate monitoring. We are continuing our discussion on remote sensing and remote sounding technologies. And in the previous class, we looked at thermal infrared imaging systems and how they can be used to evaluate the land and sea surface temperatures. We will look at one of the another application of TIR imaging, particularly for cloud detection. Now, we have said that VNIR images can detect clouds as well. In fact, in most remote sensing and sensing systems, a combination of VIR and TIR image is used to detect cloud distribution in a region of study. The brightness temperature of a cloud is approximately equal to the cloud top temperature, which is much colder than the underlying land surface. Hence, cloud pixels will be regions of low radiation intensity in the 10 micrometer TIR channels. Because the clouds are much colder compared to the land surface or sea surface below it, it will have a sudden drop in the TIR spectra intensity in 10 micrometer range. Furthermore, if the cloud is optically thick, it will have a high reflectance in the VNIR band. Hence, cloud detection algorithms are designed to detect pixels that have high brightness in the VNIR band and low brightness temperature in the 10 micrometer TIR channel. This combination of VNIR and TIR imaging helps us to detect cloud and cloud distribution on the world. Furthermore, the varying brightness temperature across the TIR bands can also distinguish between lower, warmer clouds and higher, colder clouds. And the distribution of low-lying clouds and high-lying clouds is very important in modulating the energy balance of the world and is very important for accurate climate models as well. So, this critical information is also provided by the TIR channel along with the distribution of clouds. So, here is a picture of a cloud structure over Northern American continent between two seasons. This is spring season of 2010, the top figure, and the bottom figure is the summer season of 2010. And here you can see various temperatures. So, the temperatures are starting from 20 degrees. This is basically the land surface, 20 degrees and 10 degrees. Going from -10, -20, and then light blue and dark blue are -30 and -40. These are primarily low-lying clouds. So, this white region then is low-lying clouds because the cloud top temperature is less cold. Then you have mid-lying clouds which are blue region -40, -50. Then you have high altitude clouds which are temperatures of -60. So, white to light blue to dark blue to green. This gives us a distribution of both the cloud where the clouds are located as well as the altitude of the cloud top with respect to the ground, high cloud tops and low-lying cloud tops. This is in spring and this is in summer, another day in summer, and here you can see that significant fraction of the clouds are in the white band with small amounts of blue and green bands. So, we can see in summer you have more warmer low-lying clouds than in spring where you have much colder high-lying clouds. So, this interesting information can be obtained from TIR imaging in combination with VNIR imaging. Next, we come to the second major type of measurements, that is remote sounding. And first, we will look at atmospheric sounding from satellites. So, atmospheric sounding techniques observe radiation at windows where atmospheric emission and attenuation are significant, so that information about atmospheric temperature, density, and species distribution can be obtained from them. This we discussed. So here we are no longer looking at wavelengths which are transparent to radiation, but wavelengths where atmosphere actively absorb or emit radiation. For species detection, oxygen is the most important gas in atmospheric sounding from satellites because its concentration can be used to estimate the pressure profile of the atmosphere. So, oxygen is one of the species that is detected not for finding oxygen concentration but a way to measure the pressure of the atmosphere, because we know the fraction of oxygen in the atmosphere is more or less constant with altitude. The next most important species that is detected is water vapor, which is extremely important meteorological and climatological parameter both for precipitation as humidity as well as climate governing the thermal radiation of the climate. So that is the next most important species. Then you have ozone and aerosols, which are also detected by remote sounding methods. So firstly, temperature is measured, density is measured. Among species distribution, oxygen is measured for a proxy for pressure, water vapor measured for its importance in meteorology and climatology, ozone and aerosols are measured next. Thermal infrared bands are used for measuring temperature and absorbing species like CO2, water vapor, etc. But UV, microwave and radio wave bands are also used for ozone detection and scattering from aerosols, dust particles, water droplets, etc. So the sounding techniques of course also have UV IR band, but also UV band, microwave band and radio wave bands are also used. Okay. So here we will first look at the how to measure temperature of the atmosphere, vertical profile of the atmosphere temperature using atmospheric sounding method from the satellite. So here we are looking at a satellite that is viewing the Earth directly perpendicular, so Nadir viewing. If a sensor views vertically downwards into the atmosphere at a wavelength at which the atmosphere is optically thick, then we have shown earlier when we are looking at the temperature distribution that is being observed from the top of the atmosphere, that the brightness temperature of the radiation that this satellite detects from space is characteristic of the atmosphere at a depth below the sensor that is of the order of the absorption length. Okay. So suppose the absorption length is such that it is 3 km above the ground surface. Then the temperature that the satellite will primarily detect will be the temperature of the atmosphere at 3 km above ground. Okay. So if the atmosphere is optically thick, then at the order of the absorption length, the optical thickness tau value, that is the temperature signal that this satellite will receive. Okay. So if for that specific frequency band the optical thickness is 5 kilometers, then the atmospheric temperature 5 kilometers will be detected by the satellite. If in another frequency band it is 10 kilometers, then the temperature of the atmosphere at 10 kilometers above the ground will be detected by the frequency band. So in this way, by shifting from one frequency band to another frequency band with different optical thicknesses, a Nadir viewing satellite can measure the atmospheric temperature at different vertical lengths. Okay. The thermal infrared temperature profilers normally employ the broad and deep carbon dioxide absorption fissure near 15 micrometers for this scanning. So on either side of the 15 micrometer region, there is the absorption length kind of varies as we move away from the completely absorption case to partial absorptions. So there we can change the frequency by a little bit to get varying absorption optical thicknesses and get different temperature profiles. Okay. So let's look at the theory in a little bit more detail. So here we have a satellite, we have thermal emission from the ground, which is going through the absorbing atmosphere, absorbing and emitting atmosphere. Suppose the radiation intensity is at altitude z is I nu z, and at the top of the atmosphere which the satellite is detecting is I nu infinity. The optical depth of the atmosphere at the altitude z is tau nu z, and at the top of the atmosphere is tau nu infinity. Then based on the Beer-Lambert law integration of it, as we did in the when we are looking at the transmission of IR radiation on the Earth's atmosphere in one of the earlier week's lectures, we saw that the radiation intensity of at frequency nu at altitude z is the radiation intensity from the ground, which is being attenuated by this exponential function, exponential minus tau nu z by cos theta, where theta is the angle with respect to the zenith, plus integration from 0 to tau nu z, so 0 to the optical thickness up to this altitude z, into the black body radiation intensity value at the various temperatures along this path for the atmosphere. So T tau prime is the dummy optical thickness value which changes with the altitude z. So whatever the temperature at a given optical thickness along this path by cos theta, again theta is because the zenith angle, into the attenuation of that emitting atmospheric layer and the altitude z. So tau nu at z minus tau prime, which tau prime is between 0 and z, right, by cos theta d tau prime. So this is the emission aspect from the intervening atmospheric layers, and this is attenuation of the ground emission. Okay. So we have seen this when we discussed the basic radiation theory many classes ago. In this case, we are interested in what the satellite is getting, and satellite I nu is at infinity, so top of the atmosphere, and theta is 0 because this is Nadir view. So we put theta is 0 and this as infinity, so we get I nu at infinity, radiation intensity at the detector, ground level radiation intensity exponential minus the total optical thickness of the atmosphere at for frequency nu, plus 0 to the total optical thickness of atmosphere by this term where theta is 0, so the denominator goes away. So this is the expression we have to evaluate. Okay. Now there are many cases. Firstly, if the atmosphere is very thick, this term can go to 0, and this is the main contributing term. And what this is the overall integration of all the radiation from all the intervening atmospheric layers from the ground to the top of the atmosphere, and this is a weighting function, which is a relative contribution of each of the atmospheric layers to the total radiation coming at the top of the atmosphere. Correct? This is the weighting function. Correct? So near the ground, these values are lower if the optical thickness is very high, and close to the actual optical thickness value, you will have the maximum weight. So this function, if we evaluate, will be giving us the average temperature of emission that we will be getting for this I nu value. Alright. So tau nu infinity is optical thickness at the given frequency. Now, the sensed brightness temperature over the wave band is given by this expression here. We already discussed this. So if we have a given wave band in the IR radiation, then the sensed brightness temperature at the satellite end is K2 by log of K1 by the average radiation intensity over this frequency band at the top of the atmosphere plus 1, and K2 and K1 are given by the satellite manual itself for the detector. Okay. So if you know I nu infinity, if you can evaluate the brightness temperature that the satellite is getting. So this value we already know. Okay. The actual ground brightness temperature is of course this term here. If I nu S is known, for example, from a VNIR image, okay, or so you can also find I nu S by looking at the surface temperature value. So in the TIR imaging system, we already using the TIR image that will be associated with this atmospheric sounding detector as well, we can evaluate the surface temperature already and the INUS corresponding to this. So this term will also be evaluated from the TIR based imaging technology that we discussed just in the last class. So this term is also known, and for a given frequency the optical depth is also obtained from physical evaluation alone. So this term is entirely known, this term is entirely known. This is the problem. Okay, we have to evaluate this term. Now there are ways to simplify this. In many more sophisticated algorithms, this term is directly evaluated, but we will show a more simpler technique of doing this. Suppose we assume that the sensed brightness temperature and the surface temperature from the ground are not significantly different. Okay, then we can do a Taylor series expansion with respect to the temperature value for this, because this is a function of the measured brightness temperature. This is the function of ground temperature plus a correction. Okay, if these two are close enough, then a Taylor series expansion and removal of higher order temperature dependent terms can be done to get this radiation intensity expression in terms of temperature alone. So this is an expression, this is an approximate expression only. This is the observed brightness temperature that the satellite, the remote sounding sensor is detecting. This is the ground temperature of that result, which is obtained from TIR imaging system. This is the optical thickness, which we already know. So this part is known. This is the temperature. So here it's the intensity. Here we are having an expression in terms of temperature alone. Temperature at an intermediate altitude where the optical depth is tau prime, exponential of tau prime minus the total optical depth d tau prime 0 to tau min. So this is a temperature relation only, not the radiation relation. Okay. So once again, if this is very small, then the entire TB is coming from this expression, and this will be an average temperature of the mean altitude where the optical thickness is 1. Equal to the optical thickness of the atmosphere. Alright, this we know. So this value will be T tau prime average, this value here, and this will be added to this term, and if this term is small, then TB is almost equal to T tau prime average, which will be the average temperature of the altitude at the optical thickness value. Okay. Now here the optical depth is given by 0 to infinity partial density of the atmosphere into the absorption coefficient of the gas into dz. So if this is near the CO2 band, then this is partial density of CO2, which is well known for entire altitude zone, the absorption coefficient of CO2 into altitude z, and tau now z prime is up to z prime. So these two terms are here. Okay. And this term here is the weighting function, height weighting function, and needs to be determined in order to solve the expression for T tau prime average. The weighting function gives the relative contribution of a layer of atmosphere at a given optical depth to the quantity being measured. Okay, this one I am highlighting. The weighting function, this term, gives the relative contribution of a certain layer of atmosphere at a given optical depth to the total quantity that is being measured, which in this case is the temperature. Assuming that the absorber partial density is proportional to the total pressure, which is of course true for CO2, which is a well mixed gas, okay, and the pressure is varying exponentially, that is decreasing exponentially with height, also a very good approximation as we have seen before, then this weighting function can be expressed in terms of the total optical depth, the scale height of the atmosphere. So this h is the scale height of the atmosphere into whatever is the altitude z for that given tau prime value, this expression. Okay. So this expression can be put here, and this expression can be evaluated explicitly, because now we have all the terms we need. We know the optical depth, we know the scale height of the atmosphere, so we can integrate this to get the tau T prime average. and the weighting function itself can also be plotted with respect to z. So here, this is what we have done. This is the weighting function. Note that the expression is in terms of kilometer inverse, because the scale height is in kilometers. Optical depth is a dimensionless term. Okay, you remember this is optical depth. You will see this optical depth is a dimensionless term. All right. So this is the weighting function with kilometer, and the values here are basically values of different total optical depth tau. So these are values of tau nu infinity. So what if the optical depth is 1, what if it's 2, what if it's 5, what if it's 10, 20, 30, 40, 50. Okay. So this is an extremely thick case where the weighting function shows that the main contribution comes 30 km above the atmosphere. Whereas for a moderate case, say the optical depth is 5 in a certain spectra, then the average temperature is the average at around 11 km. So near the top of the troposphere. If the weighting function is 2, then the temperature being measured is near around 3 to 4 kilometers above the surface. Okay. And the weighting function is 1, there is a significant contribution from the ground. So in these cases, there is significant ground contribution as well. For these cases, 5, 10, 20, the ground contribution is too small and can be neglected. Okay. So the values of the weighting function for various total optical thickness values are shown. We know that the peaks of the curve shifts to higher altitudes as the optical thickness increases. This peak corresponds to the altitude from which the most of the correction term is coming. Hence, this is the approximate altitude for the evaluated T tau prime average. However, the peak is fairly broad. So, the vertical resolution is poor, of the order of around 10 kilometers. Because of this broad peak, the vertical resolution of this temperature that we are getting is quite poor for a single weighting function, order of 10 kilometers. So what is done is that you either put more sophisticated weighting functions and you use an iterative procedure based on scans over closely spaced wavebands. So you put one weighting function here, another closely spaced here. These will differ slightly. So use that and use a careful algorithm to get better resolution based on the different values of T average that you are getting for closely spaced wavebands. Okay. But one of the problems that while Nadir gives a vertical profile over a certain location, the resolution is reasonably poor. So once T tau prime is evaluated, equation 10.9, this equation here. So suppose we get the vertical temperature profile. All right. Now, knowing the temperature profile, we can reevaluate this expression for a different waveband for a different absorbing species. And for that different absorbing species, we will get again the brightness temperature, the TS, and we know what this thing is. So we can get the optical thickness for that species, and based on that, we can get the density values rho I z at each and every altitude z. So once the vertical profile itself of temperature is known, the same location can be scanned for different wavebands where different absorbing species are important to get the partial density function with respect to z, and that will give the concentration profiles of the various species. And this way, starting from CO2 and getting the temperature profile, we can also get the species profiles for N2O, methane, etc. Okay. Finally, we will also look at what is called another option, which is called limb sounding and solar occultation. So here, instead of the satellite, so here is the Nadir view. We are getting the radiation directly normal to the ground. A limb view is you are getting the radiation tangentially with respect to the atmosphere. So the satellite detector is looking tangentially through the atmospheric layer. Okay, without this touching the ground at any point. What is the advantage? The advantage is the background is cold space, which is not emitting at all. So in this expression, this term goes to 0 directly. Okay. The second advantage is the dz term here is much smaller. So here basically the dz is starting from this z here to this z, which is the minimum z value, and this z. So the variation in z is within a much smaller regime because this is a tangential cut through the atmosphere. Okay. So emission from this point is at a certain z location value. Emission from this is the closest the tangent gets to the ground. So the distance of the tangent, this line from the normal to the ground normal is this one, the lowest value. This is called z0, which is important, and this is the maximum z value here. Okay, but this location is much lower than the 0 to infinity of z that we are getting here. Okay, so we have a much smaller altitude variation for the emission. Okay, what this means is, and if we evaluate this properly, is that the weighting function is very sharply peaked at the corresponding z0 value. So suppose the minimum distance of this line from the ground is 2 kilometers. So here, okay, then the weighting function is asymptotic at 2 kilometers and goes down as we move to higher and higher kilometers. And it is not, because no z0 below 2 kilometers, z value below 2 kilometers is gained, there is no value here. Okay, similarly at 4 kilometers. So you have most of the temperature contribution is from 2 kilometers here, from 4 kilometers here. So by this limp wing technique, we can actually get atmospheric emissions profiles with very good vertical resolution. Okay, so that's the main advantage, and this is what has been shown here. Okay. The disadvantage is this satellite has to be very well positioned. Even if there is a small deviation, this tangent can move by several kilometers here. Okay, a small deviation down by a few few hundreds of a degree, and this will go down by 500 meters or 1000 meters. Okay, so the satellite positioning has to be exactly accurate. And second, this is a cut through the horizontal layer of the atmosphere. So the zonal average, you are getting a kind of a horizontal geographic average of atmospheric emission through a large swath of the atmosphere above the Earth's surface. So here you are getting kind of a single vertical profile. Here you are, if you do multiple times, you are getting a vertical profile along this entire zone. So the horizontal resolution degrades, but the vertical resolution improves. Okay, so that's the trade-off. All right, but these two together help us to give good quality data for the vertical temperature gradients and vertical species gradients throughout the atmosphere. The last way that we do is solar occultation. So here the satellite is so positioned that the sun between the detector and the detector is seeing the sun through the atmospheric layers. Okay, so just as the sun is setting or rising with respect to the point of view of the satellite through the atmosphere. So then shortwave absorption by atmospheric layers, by say ozone or dust particle scattering, those things can be measured using this solar occultation method, where the satellite is doing a limb view with the sun at the background. Okay, so this is a picture of how this solar occultation picture looks when the sun is just about to rise and set, and this is the thin layer of the atmosphere through which it is rising and setting. Okay, so this is another technique of solar occultation. Okay, so based on this, you can get species measurements, temperature measurements, and density measurements. Okay. So in the last class, we will go look at ground-based remote sounding techniques, and that will cover our syllabus. So thank you for listening, and see you in the next class.